Welcome to rapid repeated integration by parts. So recall, we had our tabular integration by parts format. Where we have our u and dv. And we pick our u and dv and then differentiate on the left, integrate on the right. And that gave us du and v. And then integration by parts said we took the positive product on the first diagonal, and then we took minus the integral of the product of the bottom row for our integration by parts formula. So for rapid repeated integration by parts, this allows us to do multiple iterations of integration by parts all in one table or tabular format. So this is to do multiple iterations of integration by parts. In one table. So the general idea, we start off with our u and dv. And so we have our first u, our first dv. We do our differentiation and our integral. We get our du and v. And we would add on the product of the first diagonal, subtract the integral of the bottom row, right? And then let's say that we need to do integration again, right? So let's say we need integration by parts once more. So if we need integration by parts again, so if we need integration by parts, on the integral of v du, then we could set it up again where u this time is essentially the du we wound up with before, ignoring the dx. And our dv is the v we found before. And we can differentiate again and integrate again and do our integration by parts again on that. So we would again do positive product and then subtract the integral of the bottom row. Now, because we are subtracting that whole integral, we are going to subtract this whole piece. And so it actually would become that bottom integral. So this is the bottom row integral. From our previous integration by parts. Essentially what's going to happen is our signs are going to flip. Since we are subtracting, we are actually going to be looking at this time around, we have a negative product on the first diagonal. And now we would actually add the integral. So it turns out we can just keep running integration by parts, differentiating down the left, integrating on the right. until you get to a point that you would like to stop. I'm going to give myself a little more space just to show this next row and what the signs wind up looking like. Again, what I had here is because we were subtracting this integral, so because we were subtracting the integral of v du, those signs are now backwards from what they were. So it turns out we can just keep differentiating down the left, keep integrating down the right. We'll keep integrating down the right. Until we reach a desirable stopping point. So in terms of our table, we'll have our u and our dv. We start off with our initial u and dv. We do a series of differentiating down the left. We do a series of integrating down the right. The first diagonal, we will take the positive product. The second diagonal, because we are subtracting that integral, we now do a subtraction. That one would have a positive integral. So on the next diagonal, we flip back to the positive. And then we end with whatever the opposite sign is and the integral. So we could have positive, positive, and then a negative integral if we ended with, if we did positive, negative, and ended on a negative backwards diagonal, then we would end with adding the integral of the last row. So I have a couple examples. Let's go ahead and work through. First up, let's evaluate the definite integral from 0 to 3 of x squared e to the 3x dx. So again, the first thing we need to do is find an antiderivative. We are looking at integral of x squared e to the 3x dx. X squared will simplify as I differentiate. E to the 3x doesn't get more complicated either way. So I will take my u to be x squared. My dv will take the e to the 3x dx. If I differentiate down the left, we go to 2x. Differentiate again. We go to 2. I like to go until we hit 0. If we do run to 0. Integrating down the right. So that first integral, e to the 3x, we keep the e to the 3x. And then to undo the effects of the chain rule, we will divide by 3. Again, you could do u substitution, set u equal to 3x. You will get 1/3 e to the 3x. Integrating again, we divide by another 3. We wind up with 1/9 e to the 3x. Integrating one more time to match that 0. We would have 1/27 e to the 3x. Now integration by parts, rapid repeated, says we take the positive product of the first diagonal, negative product of the second, I need to update my screen. 1 minute. All right, so we had positive product on the first diagonal, negative product on the second diagonal, positive product on the third. That was the last diagonal. Since it was a positive, our bottom row, we will subtract the integral. Now, the reason why I like to go all the way to 0 is because there is no integration left to do. At this point, we have that the integral of x squared e to the 3x dx is equal to, we have an x squared times 1/3 e to the 3x. Then we subtract off 2x times 1/9 e to the 3x. We add on 2 times 1/27 e to the 3x. Then we subtract off the integral of 0 times 1/27 e to the 3x dx. This becomes 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x plus c. As you can see, this is way faster than having to write out integration by parts over and over and over again. So I love using rapid repeated. At this point, we have our antiderivative. We can go ahead and find our definite integral. So part 2, our next step, we apply the fundamental theorem of calculus. To find, we were looking for the definite integral from 0 to 3 of x squared e to the 3x dx. So in this case, again, we already found that antiderivative or an antiderivative. We have x squared e to the 3x, definite integral from 0 to 3 of x squared e to the 3x dx. This should be the same as, we have our antiderivative 1/3 x squared e to 3x minus 2/9 x e to the 3x plus 2/27 e to the 3x, evaluated at 0 and 3. I'm going to just factor out that e to the 3x. So we're looking at 1/3 times 3 squared minus 2/9 times 3 plus 2/27 all times e to the 3 times 3. And from that, we are then subtracting 1/3 times 0 squared minus 2/9 times 0 plus 2/27 times e to the 3 times 0. This becomes, we have 81/27 minus 18/27 plus 2/27. So 81/27 minus 18/27 would be 63/27 plus 265/27. Times e to the 9th minus the other part, we're just left with 2/27 times 1, or just 2/27. All right, so that is our definite integral using rapid repeated integration by parts. Now let's go ahead and find the indefinite integral. The integral of 5x to the 4th cosine 2x dx. up to you whether you want to pull the 5 out front or just work with it. I'm going to just leave it out front for now. So this is 5 times the integral of x to the 4th cosine of 2x dx. Working just on that integral of x to the 4th cosine 2x dx. Take for our u x to the 4th. For our dv, let's take cosine of 2x. We are going to differentiate down the left. So x to the 4th goes to 4x cubed, goes to 12x squared, goes to 24x, goes to 24, goes to 0. Again, you're welcome to stop at the constant. I loved going down to 0 just so I do all the integration within the table. We're going to integrate down the right. So integral of cosine is sine. We have a sine of 2x, and of course, with u substitution or counteracting the chain rule, we need to do a 1/2 times. Integral of sine is negative cosine, so the next one we wind up with negative 1/4 cosine 2x. Integral of cosine is sine, so integral of negative 1/4 cosine would be, we have a negative, in this case, 1/8 sine of 2x. Integral of negative sine is positive cosine, so we'll go to a positive 1/16 cosine of 2x. And of course, integral of cosine again is sine. This becomes a 1/32 sine of 2x. So again, that's differentiating on one side, integrating on the other. First diagonal is a positive product. Then we go to a negative product, positive product, negative product, positive product, going for each of those diagonals. Because we ended with a positive diagonal, we continue with our switching signs, we will subtract the integral. So this becomes the integral of x to the 4th cosine of 2x dx is, our first diagonal was positive x to the 4th times 1/2 sine of 2x. Then our next diagonal, we are subtracting a 4x cubed times a negative 1/4 cosine of 2x. From there, we are adding a 12x squared. We're on the third diagonal now, a 12x squared times a negative 1/8 sine of 2x. The fourth diagonal, we are subtracting 24x times 1/16 cosine of 2x. Fifth diagonal, we are adding 24 times 1/32 sine of 2x. And then we are subtracting the integral of 0 dx, essentially. But again, I love going all the way to that 0, simply because there's no integral left to take once we do all of our, put our table back into the equation format or formula. So this becomes 1/2 x to the 4th sine of 2x plus x cubed cosine of 2x minus 12/8 is also known as 3/2 x squared sine of 2x. Then we have minus 24/16 is again 3/2 x cosine of 2x plus 24/32 is the same as 3/4 sine of 2x. Integral, last integral, we just have plus c. So we then have plus c, and that is our integral rapid repeated integration by parts. Again, personally, I find this much, much, much faster and easier to keep track of than having to do a bunch of separate integration by parts and make sure I don't lose track of the signs. You are welcome to use rapid repeated integration by parts whenever you like. I actually use rapid repeated integration by parts even for basic integration by parts, and I just go to 0 so that I don't have to keep track of all the integrals. In the next video, we will look at a special case where the rapid repeated integration by parts never ends on 0, and we'll see what we can do then.